Hello and welcome to the second session of our drone design workshop here at SimScale. My name is Milad and today we will continue our journey through the world of engineering simulation and learn how to leverage the SimScale platform and finite element analysis for drone design. I think you know this procedure from our last meeting, and just before we start, I would like to make sure that everybody can hear me loud and clearly. So guys, in the GoToWebinar app, which we use to broadcast this webinar, you will find a button called Raise My Hand. Please click on this button in the case you can hear me loud and clearly. Great, looks like the audio is working fine. In the case that the audio quality should drop for some reason, you can also use our toll-free audio service number. On the slide you will find several toll-free numbers for different countries. Just dial the number and enter the access code you see on the slide once you're asked. Okay, then let's take a look at our today's agenda. So the topic of our today's session is structural simulation, and last week we started to talk about simulation in general and did a fluid flow simulation of the aerodynamics of a quadcopter, and today we want to analyze with simulation tools the structural behavior. So let's take a look at the agenda. First of all, I will just talk with you very quickly about some organizational things, since a lot of people joined for the first time today. Just after that we will talk about the fundamentals of FEA, and then I will show you during the live demonstration how to simulate the stress distribution inside the drone assembly. Finally, I will present your homework assignment to you for next week, and we will have time for a Q&A. Just to make sure, the idea of this workshop series is really to introduce interested engineers and hobbyists to engineering simulation, show them how to leverage our free SimScale online engineering platform for their own drone design projects. So therefore this is not a detailed training about simulation theory, but very hands-on. And this is the second out of 3 sessions, and every session comes with an optional homework assignment. And submitting all 3 homework assignments, which you can do at home, it's a simulation task, will qualify for your free certification. And yes, we will record all these sessions. Later on I will send a recording link to you. And if you need help or support, just check out our forum on simscale.com/forum. Great, so let's start with the fundamentals. In the case you have questions in the meantime, just submit them using our the question box in the GoToWebinar software. And in the case you have a question, just send it there and I will try to answer it immediately or latest during the Q&A. Perfect, then let's start. And today we will focus on a different kind of simulation, finite element analysis, which is used mostly as a synonym for structural simulation. And let's first of all try to understand what is the idea of finite element analysis. And therefore we should take a look at the image of this hook. Just imagine you want to calculate the stress which will appear inside this hook if you apply a load on the hook. And as you know from school or university, for a lot of simple problems like elastic bars, there are analytic solutions which allow us to calculate the displacement, stress, etc. inside the part. But for this complex real-world shapes, there are no analytic solutions available anymore. And what we do here is using FEA is basically to calculate approximate numerical solution instead of a 100% accurate analytic solution. And therefore we are dividing up the geometry we want to investigate into a finite number of degrees of freedom of such cells. So we are like rebuilding the continuous domain from simple geometric shapes which we call cells. And in the end what we're doing, we have some fundamental equations and for in CFD the fundamental equations were the Navier-Stokes equations which were describing the conservation of momentum, energy and mass. And for finite element analysis for structural simulations this equation is a little bit different. But in the end, we are replacing, as I mentioned, this continuous domain by a discrete model, and every of these elements is, you can imagine, it's a small piece of a structure. And since these are very simple shapes, we can now calculate the forces and strains and stresses for every of these nodes which are connecting these elements. And this is a very simple example. Just imagine we have a bar, a metal bar, and you don't want to do analytic, you don't want to look for analytic solution, but you want to apply a finite element analysis. So what you would do in the easiest case is to represent this bar by one finite element, by a beam element. So it's a one-dimensional element in the end of the day. And if you take a look at the nodes, and we know we have a force at every end of this beam, and basically we can write out this equation describing the equilibrium of forces displacement for every node. So here we have F1, and this force F1 can be calculated by taking in account the displacement of this point and the stiffness. And E is the Young modulus, which is describing in the end, which is describing the stiffness of this node or of the bar. And A is the cross-section area, L is the length of the bar. So A divided by L is something like the density, a one-dimensional density, massless density, let's say. And you can take a look and watch this derivation. There's a very nice video on YouTube. But what I would like to talk about with you more is that we have this constitutive equations. One of them is saying that stress multiplied with cross-sectional area, reference area is a force. We have stress is Young's modulus multiplied with elongation. Elongation is the ratio between the displacement of the points and the length. And using these constitutive equations, we can assemble together these equations into a matrix, and then we have a matrix K, including the stiffness. So we have a displacement vector U, and we have a force vector F. We get F from the boundary conditions, K from the material properties in the mesh, and U is unknown. And basically, we are trying to calculate the end of the FEA simulation to get a solution for the U vector, for the displacement vector. At CFD, we want to get a vector for pressure, for velocity at a scalar field for pressure, and here we want to get a vector for displacement. And if you compare the results, you can see that there is a linear interpolation between these nodes if you have a larger model, and that is very important, because just imagine if you would only use like one point, I hope you can see it, then you would have a larger difference. And in the end of the day, the accuracy of simulation is massively depending on the right sizing of your mesh, the right density of these nodes. And I hope that this helped you to get a little bit an idea about the background of FEA. In the next 5 minutes, I will show you how to simulate yourself or how to use FEA yourself for drone design. But before we start with that, I would like to talk with you about some fundamentals of structural mechanics, which I think you should know to make sure you will really understand what we will do today. So maybe everybody who knows what this machine is can raise his hand, put the raise my hand button. Yes, at least some of you seems to know it. And this is a tension test machine. And this kind of machines is used to characterize material probes. And I'm quite sure if you have studied engineering that you have used this machine on your own, or at least saw it somewhere in a lab or something like that. Great. And basically what this machine is doing, because basically, we need to, I explain to you what this machine is doing, and basically how we use it. You are creating a small material probe, cylindrical probe, and putting it into this machine, putting it into a lower and top vise, and then these vices are hydraulically, most of the times, moved away from each other, which will mean that you are straining the material, and at the same time you can measure the stress by measuring the force you need to keep the movement or to keep or to create the displacement. And if you start to do this and you measure start to measure strain and stress, you will see that first of all your measurement will look like this. It's a linear graph. And if you increase then the strain more, the next thing you will see is that first of all, let's take a look here. If you take a look at this graph, you will see that it's a linear graph, and if you divide the rise of the stress by the run, you will get the slope, which is our Young's modulus. So the Young's modulus is like a proportional constant, which is giving the relation between stress and strain. But if you continue, and the great thing is, if you stop the machine within this area of stress, the machine will immediately get back to its initial position, and also all the stress will disappear and all the strain will disappear. So as long as you're on the strain, you have this elastic material behavior, which we know from a spring, for example. But if you increase the strain further, you will notice that there will be a kind of let's say delay. So you will increase the stress and strain, and the stress will stay constant and drop a little bit, but then it starts to grow like this, non-linear anymore. And this maximum we have just in front of is called the yield strength, and that's the maximum strength you can apply or maximum stress you can apply and until you start to have material damage and plastic deformation. And this curve you can see here, it's describing the plastic deformation of the material, and at some point the material will break and crack. And then we can define it like we have this, in this area left from the ultimate strains, we have the strain hardening, and starting from the ultimate strength we have the necking, which means the cross-section of the material probe becomes smaller. And if you take a look at this elastic area, there we have in the end 3 parameters which can fully describe most of linear materials, especially metals and plastics. So we have the Young's modulus, then we have the Poisson ratio. We need the Poisson ratio because this is a one-dimensional material model, but in reality we want to do 3D simulation, and the Poisson ratio is like giving the relation between compression and decompression, and we need the density, which is not included in the graph. But if we have these 3 parameters, we can describe any material which has a linear elastic behavior. And if we have plastic behavior, we need some additional information. We need Young's modulus, Poisson ratio, and density to cover this elastic part, but this non-elastic, non-linear part, for this we need an explicit defined stress-strain curve as an Excel sheet, for example. Great, and now I think it's time for our live demo. And today we will again take a look at our drone, and here you can see a symmetrical part of the drone assembly. And today we want to simulate and to find out how many lift we can add to this design until the arm will start to crack. And if you take a look at this assembly, you see that I've painted the connecting bolts in red. And the reason is that this is a very important effect we can simulate very easily with SimScale. It's the effect of preload. And adding preload to this bolt connection will start to increase the stiffness at some point of the whole assembly. But if we do add too much preload, we can damage, for example, the parts, especially the ABS parts, because you keep in mind these bolts are made from steel, everything else is made from plastic, from 3D printed plastic. And this is what we're going to simulate today for different preloads and different lift. Okay, and what is the general FEA process? First of all, we need a CAD model. We have prepared again a CAD model, and we will provide you later on with access to this Unshaped Cloud CAD model, which you can modify yourself. And first of all, we have to start to import the model, make sure it's clean, and mesh it. Mesh means we have to divide this complex shape into small elements, and we have to be smart and do a strategic cell location or element location to make sure we only spend elements there where we need it, since the fineness of the mesh is somehow related to the accuracy of the simulation, to the local accuracy. Once we have created the mesh, which you can see here, we will start to set up the simulation. So we will define which kind of physics phenomena we want to investigate. We will define which material it's made of, what the boundary conditions are, and so on and so on. And finally, we'll do post-processing, which means we are going to visualize the results of our simulation. And now let's start with the first part, and therefore I will switch here. And I've prepared something for you guys. So this is a project, here, which is including only a geometry. Okay. Someone wants to know if there are any requirements related to the internet connection. Yes and no. Basically, in the end of the day, every computation is done in the cloud. So the computation is not depending on your internet connection, but if you want to have a good user experience, at least you should have a not too slow broadband connection. Okay, and here we can see the geometry right now. Thanks for your patience. And I just imported this geometry from OneShape, as you learned last week. And here you can see it's made up out of 5 solid bodies, and it's simplified. So it's a solid, all solid bodies. So we have the first solid, which is a bolt. The second one is also a bolt. The third one, solid 2, is representing the drone arm. And then we have the lower and the upper part of the chassis. And let me just hide the arm, then you can see what this model is made of. And here you can see this bolted screw connection, one part where everything was fused. And this is fine for our simulation. We'll show later why. First of all, we have to create a mesh. So I will click on New Mesh and choose the CAD model as a base. And since this is a FEA simulation, we can only use TAT dominant mesh. So I will add a mesh operation right now. Funny, but it's working. And here you can see the different options. And we will use TAT dominant, which means we will divide the geometry into small tetrahedral elements. And first of all, we have to choose if we want to do manual or automatic mesh sizing, and we want to do manual mesh sizing in this case. And then we have to specify a minimum and maximum edge length for the edges of the triangles. And I will start with from 1 millimeter is the maximum and 0.6 of a millimeter is the minimum, and I want the mesh grading from 3, which is moderate. We'll use a first order mesh. This means that the shape functions we are using for FEA are first order, and since we don't expect to have a lot, or we don't want to investigate what's happened during plasticity effects, this is fine. We will not use quadrangular surface elements, and if you're interested to learn about more of these expert options, we have the free FEA masterclass to check out, and we will use for a course for doing the parallel computation. But before we start the simulation, the meshing, we will add the mesh refinement here by clicking on New, and there we have different options. We will do we will not add layers, but add local element size. We will again do this manually. And here we want for some parts to have a fixed edge length of 2e-4. And a coarse mesh grading. And where will we apply this basically? Let's see. And we'll apply it everywhere where we have later the contact between the different assembly parts, because there we expect to have a lot of stresses and high gradients. And then let's start with the bolt. And the great thing is on SimScale you can select things graphically with the GUI and then add them to this list. For example, we will add it here and here, as well as here and here. add selection from viewer, and now they're selected. And then we have to do this for the arm here. And we have to do it here. We can change the representation by the way to surfaces, which makes things a little bit easier. We will add it to phase 1 and 2 here and here, since we expect here to have the lot of banding. Add it to selection, and we will for solid 3 and solid 4. We will add it here and here, as well as here and here. Save, and now everything is defined, and we can start to create this mesh and start the mesh operation, clicking on start. And since the meshing can take up to 20 minutes, I have prepared for sure a project which already includes a finalized mesh, so let's take a look at that. I will just go back to the SimScale dashboard. And open the project I have prepared, this one with mesh. And we can also open the results so far in a new tab. Guys, when you have questions, just write them down and I will try to answer them. So there is a... Fritz wants to know why exactly will the only TET dominant work for stress simulation. Dear Fritz, that's a very good question. This is related to the mathematical approach of both kinds of simulation. And for FEA, we can't use hexahedral. We can basically not use the hex meshes because these hex meshes are so-called unstructured meshes. And if we do CFD, we use a finite volume solver, which has a different mathematical approach. And this finite volume can use both structured TET and unstructured, or unstructured TET and unstructured hex, but FEA or our FEA solvers can only handle the TET meshes. Right, now I can open this project and we can take a look at the mesh which I have prepared. Great, then let's first of all take a look what we will do. The next step, we will start to set up the simulation. So we will do the general setup and define which kind of physics we want to investigate. Then we will assign a mesh to the simulation, define contacts. Contacts describes the interaction between the different solids. Then we will define the material of the different solid parts, define initial and boundary conditions, and start the simulation. So he's loading the project right now. And now let's directly switch to the mesh I have prepared. And here we can see this model is made out of 116,000 elements and 32,000 nodes. And now we are loading the mesh. Just a question of seconds, and here it is. Right, and now we can see here the finished mesh, and you can see how the refinements were automatically applied everywhere. We added them, for example, here in this area where the mesh is refined, or here around the contact of the bolts. And let's now take a look inside the mesh using the mesh clip filter. And we can define a cut plane by a reference point and a normal. So let's try to cut through the bolt connection. Yeah, looks good. And now I can click on apply, and just usually takes some seconds. This needs to be computed on our cloud infrastructure, the cut, and will then be sent back. And here it is. And here you can see how the mesh size was adapted inside this connection. Great, and now we can start to create actually the simulation. So we will create a new simulation. We will choose solid mechanics, static analysis advanced, and with nonlinear analysis true. And now, first of all, we have to select the mesh we want to use for the simulation. Can take some seconds until the mesh is loaded. And now we will define, first of all, some contacts. What are contacts and why do we need them? Since this is an assembly made of 5 solid bodies, the computer does not know how they interact and belong together. And contacts will define how this part are connected and joined with each other. And we need to create 2 contacts. One contact which is connecting the upper part of the chassis with the arm, and one which is connecting the lower part of the chassis also with the arm. So let's start with the first contact. We will decrease a little bit the tolerance of the contact. And now we have to select some faces, and therefore, first of all, I will turn off the bolts. Sorry, not the bolts, but some parts. And the first master and slave will be found right now here. So this one will be the master. And this one is going to be the slave. Save, and this connection is created. And we have to create the same for the lower part. And this is the master. And this part is the slave. Perfect. Now we have defined the interaction between the parts, but for the connection, the bolted connection, we need to define something else called the physical contact. And that is what I'm going to do right now. So first of all, physical frictionless should be changed to friction penalty contact. Then we can keep this as default values, but we will use a Coulomb coefficient of 0.3. We will add frictional clearance. And at the end of the day, we also need to apply it to some faces. And for the slave clearance, we need to define a function so that we can variate the pretension of the bolts. And therefore we will add this kind of formula. So I will change this to formula. And then it's 0.0008 multiplied with our pseudo time. This is important to understand. This is a static simulation. This is a pseudo time. And if it's smaller or equal to 1t plus 0.0008 multiplied with t larger than 1. This is our operator, so this will give back 0 or 1, if dependent if the expression is true or not. And then finally we have to apply it on some faces. So let me select them first and then show you which they are. This is quicker. Can change it by name. Where is it? There. And basically what we have to do is to apply it now. So we have first of all to define the master faces, and the master faces can be found here inside this bolted connection, and the slave are the inner surfaces. And since this takes some time, so you have to find out all the surfaces, and it's the same process like the standard contacts, and we are running out of time. I will show you that in the step-by-step tutorial. And then the final thing you have to do is to define materials for the different parts. So you can import it from the library. We have ABS parts made from plastic, so the parts 2, 3 and 4, which are the arm and the two parts of the chassis. And we have to add material steel. But we can also look on the material library here. Oh, sorry. 0 and 1, so it's assigned to the remaining two bodies. The final thing we have to do is to add constraints and boundary condition. So for the constraints we have first of all the symmetric boundary condition, which we can select here. Just change this to symmetric plane. Done. Then we need to fix also this node for make sure that our symmetric boundary condition is correct. Change this to nodes and change this from fixed to port to fixed value. And here it's important that we will only constrain it in X and Z direction. This is done. Change this to nodes, sorry. And finally, we need to add elastic support for the lower faces of the bolts. So this will be not fixed but elastic support, which means it can move. And here we will choose this faces. We have a stiffness of 25. And now really nearly done. The only thing which is missing is the load. We can add here a force, and it will be in my direction following this function. Put it the wrong place, sorry. And it here. And now we're basically done. And we're finally to apply it again on this face here. Now we are basically done. Everything is set it up. We just need to adapt the simulation control. This is all fine. And we can add some result control items if we want. And what I will add, for example, is not a solution field, but the volume calculation of the maximum stress for the drone arm. Changes from displacement to stress. And now we're done. We can start the simulation and receive the results. And since this will take some time, about 20 minutes, I have prepared the project including the ready results. Well, this was quick. And this run creates, in simulation project includes several runs. This run has the exact same setup we created right now. It took 22 minutes. And let's take a look at the results. First of all, we have, for example, this diagram showing the maximum minimum von Mises stress in the drone arm. And as you can see, the maximum stress which is occurring is around 38 megapascal, and the yield strength of ABS is between 42 and 45, which means that this is still under the yield strength, and this part will not crack immediately. But if you would further increase the lift, I think we would start to see the cracking. And we can also take a look, for example, at the displacement of the arm. And here you can see that the maximum displacement is like 0.5 millimeter. And we can also take a look at the 3D results here. Now let's, for example, change the visualization to von Mises stress, and then we can change the range from a custom range in a way that the maximum, so that the yield strength becomes red in the color bar, and we can see everything which is red would mean a critical yield stress for the ABS parts. And here you can see like that here this will last. The higher stresses in the steel is okay. And what you can also do is visualize the displacement, for example, with wrap by vector, which means you will wrap the whole geometry by the displacement vector. And if we increase the scale factor to 5, for example, you can see like the difference between the how it will bend. Okay, perfect. Then I think we can do a wrap up for the post-processing. I should show you how to apply the wrap by vector filter, how to change the legend. You can also change the time step here and just jump to different states of the simulation and make an animation yourself. Well, okay, that's it. And now I would like to introduce your homework assignment to you, and we have time for your Q&A. So your homework assignment is to do basically exactly the same simulation and simulate the structural behavior of your drone arm design using a parametric model which we provide. What does it mean? We will again give you an easy to edit parametric on-track model where you can change the size of this cutouts. And you should set up exactly the same simulation we showed you and investigate for at least one design at one given preload how the structural response of the system is, let's say, and perform a simulation on your own. On simscale.com/drones you will find again the tutorial. I can show you how this is looking like. So let's directly switch to the forum. And if we go to this drone design category, you will see here. Oh, sorry, that was too quick. You'll have a tutorial describing every step in detail. And yeah, so I hope you will work on it and have a lot of fun. And we have, as I mentioned, prepared a parametric model, which you can see here. And there you can just change the thickness of this cutouts with one parameter, with one number you change. And so every one of you can simulate his individual design. Great, thank you very much for being here with us today. And now it's time for our Q&A. So I think Krishna, my colleague who joined me today also and answered some questions in the background, has answered most of them, but there seems to be some new questions, and I am happy to answer them. So, are there any new questions? Okay, the first question is by Orzetist, and he wants to know, does the ABS material option incorporates the special structure in example layer of 3D part? Orzetist, yes and no. Basically, we are using isotropic models, which means that we are not directly considering the layer structure of the printer, like the height and the width of the layers. But the good thing is most of filament producers provide you with, let's say, translated material behavior. Just to give you an example. If you Google for, I'm quite sure, exactly, for example, here this is a paper which is describing this, and basically what they do, they print probes with defined structure, like I showed you for the tensile experiment, and then use this material function. So they are covering the microscopic material behavior by microscopic numbers. And this works quite good. Antik wants to know if you can import non-on-shape models into SimScale. Yes, for sure. You just go to the mesh creator, go on geometries, and instead of import you click on upload, and then you can upload whatever you want. Step, IGES, BRIP, or STL files. And soon we will support a lot of native CAD formats. Then Bob wants to know if I can discuss why I selected the master and slave the way I did. Bob, that's again a very good question which is asked every workshop or every webinar, which is covering also contacts. And basically there is not, it's more a rule of thumb, like there is no right or wrong. And basically you should choose the master and slave in a way that the master is, the slave is following the master. So for example, in this case, you should take for the master a part where you think or a face which will not bend or move a lot. But in this, for this setup, you could also change master and slave. I don't think it would make a big difference. But there are simulations where the right order of master and slave has a big influence. Okay, thanks. Are there, let's see, there are some more questions. Sorry guys, but I just have to Pierluigi wants to know what's about hyperelastic modelization of structure. This is also possible. There you just have to change the material behavior from linear elastic to hyperelastic. And Abdul wants to know what master and slave mean. Master and slave in this context mean which surface is following the other one. You just have to imagine, let's say the arm would massively change its shape. Then this would mean that it would also force the chassis parts to change the position because they cannot intersect, for example. And then the master slave is, the slave one is that face or this that body which is following the master body. Pierluigi wants to know if there is a preferred web browser. Basically, we support a lot of web browsers. You can use Firefox as well, but we are not recommending to use Microsoft Explorer. Bredon wants to know, how would this integrate with the propeller aerosim? Could you simulate prop RPM increasing until the material fails? Yes, that's something you could, for example, do. But I think it would go the other way around. You know that's the weight of your drone, of your parts. Then you would try to optimize the propeller, which generates enough lift, and then you can use the simulation to make sure that your arm is light and will not crash. Anwar wants to know how physical contact can impact the degrees of freedom of the structure. Answar, can you please explain your question a little bit more in detail? I think I don't get it. Don wants to know if the instruction gives the initial forces from the propeller. Not the exact force, but it's a similar force, Don, similar magnitude. And let's see if there are, but I think that are all questions we have right now. And if you get a question in the meantime, you can also post it into our forum. Okay, then I would say thank you very much for being here with us. It was a great pleasure. Thank you very much Krishna for helping me out with the questions. Hope to see you next week. Work on the homework. And in the case you're struggling and need some more time, just reach out to me and we will find a solution. And don't forget, today 12 p.m. is the regular submission deadline for session 1 homework, which you need to submit to get your certification of participation. Thank you very much. Have a nice day and a nice weekend. See you soon. Bye.